All right, Physical Organic Chemistry, CH 8553, Take 1. This is relating to section 7.2.6 in our textbook. We're going to discuss how entropy impacts reactions. Delta S, entropy. Delta G equals delta H minus T delta S. Now this can be delta G0 or it can be delta G transition state. What we're going to discuss is delta G and delta S transition state. Let's have a perspective first on entropy. Remember, entropy equals disorder, and everything moves toward more disorder. So let's consider two simple reactions that we've looked at many times before. The first, an SN2 reaction, a simple nucleophile and a simple electrophile. We're just going to do a straightforward halogen substitution. We would push the arrows like this. This would lead to a transition state that we've all imagined before that has a pseudo-trigonal bipyramidal carbon where we have partially made and partially broken a bond. We've partially made the bond between the electrophilic carbon and the nucleophile, and we've partially broken the bond between the leaving group iodide and the carbon. And of course this continues If we think about this reaction in the transition state, of course, we go from two particles to one particle in the transition state. And so we would expect a very negative entropy value. In fact, that we'll see in a few minutes will be the case when we look at these things quantitatively, because we're going from more particles to fewer particles. That means we are going toward order instead of disorder, because more particles is more disorder. Second common reaction that we're all familiar with is the SN1 reaction. A T-butyl chloride dissociates chloride, and in the rate determining step, the transition state, we're breaking that chlorine bond and in fact produce a carbocation plus chloride. And of course we're going from one particle breaking a bond, it's dissociating and giving us two particles, so we expect an increase in entropy. And of course this was a decrease in entropy. And so entropy can give us insights. The entropy for the transition state of a reaction can give us insight into the structure of those. So now we're going to look at this quantitatively to a degree. This is table 7.1 from your textbook. Some reactions that we're all very familiar with. First, the acid catalyzed hydrolysis of an ester in water. Okay. The relevant arrow pushing moving toward the transition state is pictured on the right. The nucleophile attacks the carbonyl, and of course this will produce a tetrahedral intermediate. We take two particles, they become one. Of course the water and the protonated ester have to lose a lot of their transitional and rotational motions in order to align properly for the transition state. And so we see a very negative, that is a decrease in entropy, a value of negative 26 EUs. That's entropy units. That's the typical way EUs that we talk about this. It's not a euro. We're not in Europe today. Okay. A second reaction. Acid catalyzed ring opening of ethylene oxide in water. This is a classical SN2 reaction, and we see that the entropy is still negative, although not nearly so negative as in the case of the ester hydrolysis. Here's another hydrolysis reaction. In this case, it is the extrusion of water in this acetal. So this is acid catalyzed hydrolysis of an acetal. Now notice this is the glucopyranoside, and that's the classic acetal functional group here. Of course, we can imagine this as the lone pair from the oxygen kicking out the methanol molecule, and of course we're going from one molecule to two. So we would expect an increase in entropy, and so we see here a positive value for these. Again, some more classical reactions. There is a formation of a carbocation in number 4 here, where pyridine is methylated with methyl iodide. This is a reaction that can happen, for instance, in a parallel on your DNA if you were to happen to get methyl iodide on your skin. So in my lab, when we use methyl iodide, it's a double glove experiment. We have latex gloves that fit snugly and then larger, thicker latex gloves over it because we don't want to methylate our DNA. That could lead to problems. Okay, and I would suggest in part here the reason for the larger negative entropy is that we're creating charge at the nitrogen that becomes effectively permanent, and so there's probably some solvation issues involved here because solvation can be a very big issue as well. Here's that T-butyl chloride dissociation that I introduced this section with, and we see that it has a positive entropy at the transition state because we're going from one particle to two. All right, and then I want to do one on the radical reaction pictured here at the bottom. We are, of course, breaking a bond and going from one entity, chemical entity, into two radicals, two oxygen radicals, and so we see a very positive delta E. And so we can take data like this and ascertain if it is consistent with, and remember that's our term, consistent with the observations and the hypotheses that we propose. All right, that concludes this mini lecture on section 7.26.